While people finish trickling in and settling down, we can get started. So it's our pleasure today to have Ellie Pavlick as our speaker of the Kempner Institute Seminar Series. So
Wait up, we're starting.
Thank you. So Ellie is an assistant professor of computer science at Brown, computer science and linguistics at Brown, and she's also a research scientist at Google DeepMind. She has a PhD in computer and information science from UPenn and bachelor's degrees in econ and saxophone performance from Johns Hopkins. At Brown, she leads the LUNAR group, which stands for Language, Understanding, and Representation Lab, which seeks to understand how language works and to build computation models which can understand language the way that humans do. And what is sort of very nice about Ellie's and her group's research is that they take this behavioral approach to language, which allow them to cross disciplinary boundaries into cognitive science, neuroscience, and philosophy, which I believe will be in full display in the talk today. So with that, let's welcome Ellie and take it away.
Thank you. Yeah, it's great to be here. I've already had really enjoyable conversations with many of you, so it's been a lovely day. So shout out to my students and collaborators. So yeah, the kind of theme or the reference in the title is to this kind of classic debate, which people may or may not be aware of, between neural networks, what we call connectionist architectures, and symbolic systems. And I won't really go into the details of the debate. I think the more important part that I want to talk about today is the fact that current thinking, I would say, in AI is fairly nuanced about this matter, where we kind of assume there are different types of systems in cognition and in artificial intelligence that have different types of strengths. So on the one hand, we have neural network systems that we think of as being good at things like kind of semantic associations and perception and kind of squishy reasoning. And then we have symbolic kinds of systems that are important for things like compositionality, few-shot learning, and logical reasoning. And this is a pretty widespread sentiment, I would say, in the field, is that there's kind of different types of systems with different types of strengths. And what I want to focus on is mostly this kind of the right-hand side of this, like why the symbolic piece. And there's not like a very clear definition of what a symbolic system is, but there's definitely a set of types of properties and behaviors that get referred to when people appeal to the need for symbolic representations and architectures and systems for cognition and for intelligence. So one of the really commonly cited types of categories of things where you need symbols is stuff like logic and compositional reasoning. So this idea that we have kind of small components in the world, like our complex concepts are built up of simpler concepts, and we can kind of combine these together to think increasingly complex and bigger types of thoughts. And these kinds of abilities like compositional reasoning, logical reasoning, are often cited as being really central to how we do things like fast learning and generalization. So because we can generalize compositionally, we're able to move into new domains efficiently because we're recombining known concepts. And because we have these kind of inductive biases for things like logic, we can learn quickly without having to do this kind of slow incremental association. And then the kind of third, and these are all kind of interrelated, I would say. So this kind of third piece that's often cited is this structured representations. And this is this idea that we get things like compositionality and fast learning and generalization because the representations themselves are structured in a way that is kind of compositional and modular that can be recombined. And so, like I said, these things are kind of, it's not like these are the three pillars of symbolic systems. I'm kind of gesturing at the themes that come across when people are talking about why we need to integrate symbolic components with neural components. These are the types of things that neural networks don't necessarily give us and where we would want to impose this kind of symbolic architectures. And they kind of mutually support and reinforce one another. So the argument that kind of is, I would say, in the background of a lot of the work that's going on in my lab and that I kind of want to start to articulate today is that basically neural networks, which when I say neural networks, I mean models that don't explicitly have what we would traditionally call symbolic components. Increasingly, they're behaving as and doing the kinds of things that the behaviors that we've said needed symbolic components. So things like compositionality, and logic. And perhaps more surprising to me, it's also the case that their representations appear to have a lot of the properties that we've traditionally said are properties of symbolic systems. So things like kind of content independence and constituency structure and things like that. And so the kind of general thing is this must mean something. Like this must be important because we have this very traditional dichotomy between the kind of the neural stuff and the symbolic stuff. And now we have a thing that on its face is neural stuff and it's acting kind of like symbolic stuff, and something has changed, right? The problem is that it's not exactly clear what it's telling us. And so I'm saying I'm like kind of trying to articulate this argument today, and I've given a few versions of this talk. But I like the thing I want to kind of that I'm excited about and I want to get thoughts on and discuss is kind of where are we going with this and like what does this look like moving forward? Because I think that there's a takeaway here already with what we're seeing in AI, which is like we have this very traditional narrative that has been kind of the conventional wisdom for a while. And I think it's missing some really important nuances that probably feel like nuances now, but I think if we get right, would be quite profound for changing how we think about the core structure of cognition and of artificial intelligence. And we should really be focused on figuring out what exactly that is. But the problem is there's so much we don't know. And so there's like sometimes this feeling of needing to rush to the takeaway. And I think this is kind of holds up what is a very powerful position to be in, which is if we can try to study these systems we have and try to figure out what's going on, we might be able to tap into something much deeper about how we think about these things. So my general takeaway is I'm feeling like the immediate future is more about describing how these systems work without trying to say how they should work or kind of jumping to an assumption about how to fix the problems. So that's kind of my high level outline. I'll go into some more details on specific projects. A few kind of caveats and disclaimers. So one is it's not a super high level talk, but I'm not going into tons of technical details about the projects because I wanted to illustrate across a lot of this kind of converging evidence from different types of studies that suggest this kind of symbolic like behavior out of the neural networks. So there's several projects maybe hanging together in a talk that I wouldn't otherwise put together in a talk. So I'll give a higher level, but if you want more technical details, just ask and we can go into it. It's also not really a survey, like I'm just talking about my own work, but I know a lot of great people, like some people I called out on that first slide and kind of throughout. There's a lot of other people working on programs that could give this same talk, but only talking about their own work, right? So I'm highlighting my work, but I think this is kind of an emerging consensus narrative across many different people's research if we look at what's happening in the field. And then the kind of hardest thing I think right now about having this discussion, and I talked to several people about already today, is that it's like we're kind of seeing evidence that there's something new and something changing here about neural networks. They're behaving in a way that's kind of not consistent with the traditional narrative. They're structured in a way that's maybe not consistent with the traditional narrative. But we don't actually have the upshot yet. And so there's this kind of like, so what exactly is the point? And we don't know. And so it can either feel like it's a misdirection or people can feel annoyed that it's not consistent with a particular theory. And I think that's all still kind of up in the air. So it's more just like I'm trying to gesture at like where I think things are going. But I don't have the satisfying and here's the main point yet, but hopefully in the coming years, collectively we'll get there. Okay. So I'm going to kind of talk about these three kind of, I guess, properties or characteristics of symbolic systems in sequence, one at a time. I'm using a few illustrative starts. So starting with logical and compositional reasoning. So on this project, we were looking at a specific concept learning task from Steve Panditosi et al. In 2016. And this is the way this task is structured is basically human participants are shown some set of objects and some of them are highlighted and they're given a kind of nonce word descriptor. So these ones are woodsy. And then they're asked to say which of the ones in this set are woodsy. So I don't know. People can shout stuff out. There's not a nice way to raise your hand, but people can have guesses. And so you would maybe have guesses. Maybe you think triangles, or maybe you think yellow and green things. If I now tell you this, You're going to refine your hypothesis. Hopefully, maybe you're stubborn. You're like, I think it's still triangles. Like that's the way people are. But so now maybe you're like, okay, it's yellow or green things. And now you have this. And I'm not going to tell you what the answer is here. But there's actually quite a lot of rules that could be consistent with this. So this is a concept learning task where you're trying to infer how would people reason about these novel concepts in and revise their updates over time. And this is a task we wanted to study because this has been used as kind of a paradigmatic example of a case where people use kind of logical structured compositional reasoning. So specifically, the model that was proposed in the paper that introduced the task is this Bayesian probabilistic language of thought, which basically models the inference procedure as you look at something like this and you infer some kind of rule represented in something like lambda calculus. So here you get something like this is the rule is yellow or green. And so they experimented with lots of different sets of logical primitives and then used a kind of like bootstrapping procedure to do inference over them. And in this work, they showed that it had in the case that used kind of traditional logical rules and primitives and things that had a very good fit for the human data. So this is showing kind of a correlation in the human confidence and the model confidence. You can see it's like almost too good. You almost feel like someone fabricated the data. And they show some examples of the kind of correlations over the human learning trajectories, right? So here you have the black is a human and the red is the one with a full Boolean logic. And you can see that it's really nicely matching the peaks and the troughs of the human learning as they get more examples. So you get this like really nice example of like, it is like a classic symbolic story of kind of how the mind works, which is that you have these logical primitives and you're running inference procedures over them. And at the, I would say like at the time that this paper was published and kind of until recently, it's been the case that neural networks just like suck at this. They're just not good. So it didn't even like make sense to compare against them because you like train the model over many sequences and it kind of just memorized random associations between specific inputs and outputs. And it's not even competitive. So it wasn't really in the part of the conversation. But increasingly now we have better and better neural networks. And so we're wondering is whether large language models might be able to solve these kinds of tasks in context, right? Because large language models, you don't have to train a model kind of one example at a time, but you could come up with a text version and give something that looks very comparable to what the Bayesian symbolic PLOT model was given. So you can have something that's closer to an apples to apples comparison between this neural model and this Bayesian model. And here the pre-trained model is like the large language model is coming in pre-trained, so it has an inventory of concepts. Granted, we don't know what they are, but it's more comparable to the Bayesian model, which has this inventory of concepts from which to draw when it's doing this inference. So we have this text version of the task. It's basically identical, but we're using a text-only model. So we describe the objects as something like medium blue circle, large green triangle, large yellow triangle, et cetera, and then tell it which ones are WUDSI, like group them as true or false, and then prompt it with the following one. And then kind of high level takeaways, like, so first check is in terms of just accuracy, where accuracy is consistency with the underlying rule that was intended, the logical rule that was intended. It's worth noting that there's no such thing as like a true label. Like there might be multiple rules that are consistent with what's been shown, but this is like how often do you match the rule that was used to generate the data. And the best models we're looking at, including some of the open source models, are on par with humans in terms of accuracy. That alone is not that interesting. It's kind of a first check. What's more interesting is that the models actually correlate with the human learning trajectories as well, if not better than the Bayesian models. So there's a little bit of subtlety here. So this is looking at kind of the correlation over the learning trajectory. So as you get new examples and you update your hypothesis, how does your accuracy change? If you take the, I should say this is, I think, the Gemma model, if anyone cares. If you take the models off the shelf, they're not super, they have like reasonable but not excellent correlation. If you tune the model with some of the human data, and in particular the same data that was used to set parameters on the Bayesian model, so there's still kind of fairness, I would say, with what amount of kind of fitting to the human data is allowed, then you get very high correlation, and in fact better than the Bayesian model, as well as an LLM augmented Bayesian model from follow-up work. And so if you look at this kind of correlation, you can see something like for like this is for the large language model versus the PLT, you can see not just the stronger correlation, but in particular, this kind of nice pattern where as the LLM is getting more accurate, it's also tending to be more human-like. So like higher correlation with the human model corresponds to higher accuracy. So when the model is less human-like, it's also getting it wrong, right? Which is different than for the Bayesian model, which is sometimes guessing the rule correctly, but in cases where the humans wouldn't. So in kind of this low correlation. So you see this kind of tighter fit to the trajectory, as well as this kind of nice property of being more human-like in the cases that it's succeeding. So yeah.
An instance, or is that from the trajectory?
It would be a trajectory, like one rule, the trajectory over one rule. So you take the R squared over the whole trajectory, and then the accuracy is basically how accurate is it in the last part of it. Yeah, I had hidden, so I wanted to see if I had an example of what the trajectory looked like, but I think I moved it to backup slides. Let me show. So you can see like this is kind of like an example of a correlation and trajectory where you can see this gray line is the human, and then the blue line is the language model, and the orange line is the Bayesian model. And so before, the success of the Bayesian model was like it's fitting the peaks and the troughs of the human learning pretty well, and you can see the LM is fitting those peaks and troughs even better than Bayesian model. So sometimes where the Bayesian model kind of overreacts to a single example, and the language model is doing a better job being more measured here. And I think it's interesting to look at these. In the original Bayesian paper, they interpreted this kind of match to the troughs, particularly as saying that that the troughs are evidence that the model's like revising its hypothesis, and if you're fitting that better, this is evidence that the Bayesian model has a similar kind of best so far hypothesis and similar revision. And so if we take that same logic and apply it to the LLMs, it would suggest that LLM has a similar working hypothesis. Now, whether the logic totally follows through is an open question, but I think it's, kind of granting the same interpretation to the LLM as to the Bayesian model. We kind of take this fit seriously. Let's see. So I think that's kind of interesting and kind of a more qualitative type of follow-up, because you can say that maybe the large language models are kind of approximating the Bayesian model. Like maybe these are kind of the same system that are just one's maybe a slightly better fit for some reason. But if we kind of look qualitatively, it doesn't seem that that's the case. So at least, and I'll give some caveats with this analysis, but they seem to be using different types of rules in a way that might be interesting for trying to model humans. So in particular, so I actually fight pretty hard with Roman Feynman, who's my collaborator on this, wanted to do this analysis. And I was like, no, that's such a BS thing to do. And then he convinced me that it was compelling. So what we basically do is just ask the LLM, what rule are you using, right? Which is, from my gut reaction, is like, oh my God, that's such a stupid thing to do. Like nothing guarantees you that the LLM will tell you anything useful if you just say, what rule did you use to answer that question? But actually, it's very interesting that almost like very high, I forgot the numbers, it's on a backup slide, but like 98% of the time, the rule it reports using is consistent with the predictions it made, which is very, very interesting. So we're going to just take it for a moment and say that there's something to the rule that it's reporting to use. And we're currently working on following up why this would be constrained to be related. So we can basically say for the PLOT model, we can take like the maximum a posteriori rule that comes out of the system and say which rule is that model essentially using or inferring from the examples. And then you can say for the LLM, what rule are you using? And you can say, are these similar different rules? And you can see interesting kind of qualitative differences. So in particular, like in this case, the examples, the rule is supposed to be not circle, and the Bayesian model picks not circle, and the LLM picks triangle or rectangle, right? And both cases, obviously, this one is not the same, but in both cases, they're 100% consistent with the evidence you've seen so far. So if you've seen some examples of things that are not circles being highlighted, it's actually a meaningful difference whether you infer the rule to be kind of tight to what you've seen so far as like, it's just exactly the things I've seen, or if you kind of generalize and zoom out and say not circle. In this case, the Bayesian model is doing this more general thing of saying not circle, and the LLM's doing this tighter read, right? And we see this similar kind of pattern in other cases. So like circle or blue, again, these are cases where both are truth conditionally equivalent based on what's been seen and consistent with the evidence, but are obviously meaningfully different rules, like circle or blue versus blue or yellow or green circle, right? So LLM being a much more conservative, I would say, about generalizing. And you can also see examples where where both models pick things that are not completely consistent with the evidence so far. The LLM does this because it's unconstrained, nothing forces it to be consistent. The Bayesian model does this because it has other kinds of trade-offs, like a preference for low description length and things like that. So it's not, so it also is forced or not forced to be consistent. And so again, you see this kind of differences in how they resolve these conflicts. So I like to kind of open with this study to just make this point that like, we can take these examples of tasks that even pretty recently neural networks weren't even considered an interesting model to study in these tasks. And when we look at them in the context of modern neural networks, things like large language models, they're actually solving the tasks in a way that is competitive with, if not better than, our best other models, and perhaps interestingly different. I was saying I'm kind of highlighting a single example, but there's lots of other examples that you could use to say the same kind of pattern is happening. So I think the work in analogical reasoning, I think Taylor Webb's work has been really interesting here, showing how large language models do a really nice job of fitting human behaviors in analogy across a lot of different types of analogy problems. There's work on reasoning and inference. I really liked Ashita Dasgupta's work on this kind of a thing where you can have language models doing a nice job fitting humans' kind of error patterns and content effects for making kind of so-called logical inferences versus heuristic inferences. And maybe like one of the best ones is literally just language. Like it is obviously the case that large language models are very good at producing language, much better than any other models we had before. To kind of shout out some specific work, I think Alex Horsta is doing really cool stuff on like language acquisition with language models. And so there's a lot of these kinds of phenomena, and each one you can kind of pick at individual studies having this flaw or that flaw, but kind of collectively across them, it's just the case that we have language models that are neural network models that are suddenly doing a very good job producing and kind of at least simulating human-like behavior across these kinds of things that prior to this we assumed would require this kind of symbolic structure. So that's like the kind of, I think, first thing that kind of gives pause is just like empirically, they're just good models of this, right? There's also a lot of work that's been showing how they can simulate other kinds of existing models, like Bayesian stuff that I think is specifically relevant that I want to call out. So the kind of intermediate takeaway of this kind of first piece is just that when we start talking about why we might need symbols and why we might need symbolic structure in our systems, it usually starts, like the argument starts with appeals to behavior. You say like, if you want systems that can do logical reasoning, that can do compositional reasoning, I think Jerry Fodor's phrase was like, symbolic models are like the only game in town. There's just not other stuff that can kind of do that. And this is just objectively not the case anymore. Like we just have other systems that do seem to explain this kind of behavior. So this is like kind of an essential first step here. The problem and the pushback that always comes up, and I think rightfully so, is like, we don't really know how they work yet. And so we don't really know what this means. Like, isn't it possible that the language model has just learned to implement the symbolic system exactly as we already knew it was, and therefore it says nothing new about the theory? Like, perhaps. Or isn't it possible that it's just using a bag of tricks? Like, perhaps. But since we don't really know, we can't really dismiss them yet, right? So I think this is kind of, at least for me, this part that gets really exciting is like, I feel like there's almost like a obligation now to figure out what's happening and why these systems are succeeding, so that we can come back and decide how it, if at all, it's relevant to our cognitive theory. As that kind of motivates, I think, the follow-up work on trying to understand the mechanisms that underlie these types of behaviors, because at least now, just empirically, they're a good fit and they're kind of in the running. This would be a great pause for, yeah, go ahead.
It's a bit of an open-ended question, but in the result where you ask the model to train everyone confused, how do we know that it's using the symbolic approach to solve the problem versus first finding the symbolic role that fits the prediction that it already made?
Yeah, absolutely, we don't, right? So this is, I think, this kind of, I had a long argument with Roman about this because I do a lot of work on interpretability, some of the stuff we'll talk about next, and like, it kind of bothers me because when you try and just prompt these models and ask them what to do, there's no a priori reason that there's any at all connection between these things, right? It could be like when you asked it to solve the problem, it just uses its problem solving mechanism. When you ask it to explain it, it pulls from some other part of the distribution, from Reddit posts rather than logic, like who knows, right? So there's nothing that constrains this. And so a priori, you definitely can't trust it. So that's why we said, well, let's first start by saying, like, if it does give it a rule, is it at least plausible that this is a rule it's using? As in, like, is it consistent with what it did? And is it consistent with the data? And it's true, it is. So then what kind of the discussion we had was like, now there's kind of a parsimony argument, which is like saying that there's no kind of causal connection between the rule it says it's using and the rule it actually used is like, and yet they agree with very, very high probability seems kind of harder to explain than just assuming that these things are intimately connected. Now, it's true that you can kind of do this like post hoc explanation and it's not causal in producing the rule. Like, that's true, right? So we're doing this kind of follow-up of trying to find the piece of the thing that you can manipulate that will both change the rule and the prediction, right? And I think I'm not sure what this will show, right? So we're trying to follow up on this. So yeah, this is why it's kind of qualitative follow-up and not. Yeah.
Because it could be that, it has non-symbolic system one processing where it generates, and then it's very good symbolic for everything.
Yeah. Totally.
It could be that it, uses different levels of
Yeah.
symbolism.
Yeah. Yeah. And actually the next thing I'll talk about is a bit system one, system two. I think that's very likely. But I also would say, I don't know that that isn't what humans are doing, right? Like, I don't know that so we're also going to probably, like, we wanted to follow up on the human side of this too. I have this feeling that humans gist this too. Like, if you have something like yellow or green, people are probably like, might have that rule. But when some of these rules are bizarre, it's like, the only shape of its kind in a set where there are at least two smallest shapes or something bizarre, right? I would be shocked if people would explicitly represent that rule. So they're probably like going on vibes. They're like, this one seems like the woodsy one. But then if you ask them after the fact, they could probably articulate. And Pianetosi did collect data on what rules people say they're using, but they said they were hard to interpret because people would just say like the small one, which was like ambiguous and you couldn't tell, right? So I actually think they're probably, this is exactly the kind of thing that I think we could get out of analyzing how an LLM does it that could actually lead to theoretical predictions about humans that we couldn't get out of something like the Bayesian system. Is like this kind of messy relationship between the implicit and explicit reasoning. Yeah.
So very closely related to what you just said. Is there some experiment that you could do to determine like if the LLM actually does something with the model or not?
I would say like either trivially yes or trivially no. Like, part of the problem is like, does something symbolic? I don't think symbolic is in itself a super well-defined word, right? So what these, maybe the subsequent the studies might kind of speak to this is like, what type of a mechanism might be in play here that we might consider symbolic. I should also say, there's like a definition of symbolic which just succeeding on this task, right? Like, I think one of the ways that the theory is kind of advancing, or that I see the LLMs as forcing this theory to advance, is that like, when we considered symbolic systems the only game in town, success on a task like this was evidence of being a symbolic system, right? And now when there's something else, we have to be like, oh, okay, wait, what actually is it that we are looking for, right? Because there's like, there was no other alternative explanation besides being something like the Bayesian system that would explain how you get this kind of behavior. So there's some kind of like there's this nice paper that I quote, not here, but this Quilty Dunn paper called Still the Best Game in Town, about like language of thought type models. But it kind of describes these like clustering effect of symbolic properties. It's like symbolicness is almost more of like a syndrome, right? It's like, it's some collection of properties that a system would have, but it's not like there's a symbolicness gene that you can identify. So I would say that like, yes, probably if you're not willing to accept that like success on this task is symbolic, but you want to ask for something more about the mechanism or the representation, then I would say these next two sections kind of speak to that, not directly in the context of this task, but another way. I don't know if that helps. Yeah.
Just the specific question, were the models, the open weight models that you used, were they pre-trained only or were they like fine-tuned RLHF?
Oh, yeah, good question. I forget which ones are which. We did like a mix of the different ones. I don't think we saw. No, we probably did see it. I'm sure the instruction tuned models did better because there's quite a bit of instruction required here. So I don't remember. I think Gemma is instruction tuned, but I forget which of these are and are not instruction tuned. What? Yeah, yeah, but GBD2 wasn't that good. Yeah. Yeah.
See, talk about like so more architecture-centric perspective, like intentional versus symbolic structures or symbolic architectures, right? And that would be the question that you said like you're going to dive into, like how does a language model do this task? But I think like from an architectural standpoint, like another question which is possibly also more related to the architecture perspective is how does the model learn this, given that it was not designed to learn such a like of course one answer could be that it's just the data works this way.
Yeah.
Inevitably have to learn this thing.
Yeah.
Yeah. Do you have any thoughts on that? Is like did we implicitly just bias our architecture to learn this as well, like attention creation?
Right. Yeah. Yeah. I think this is really, this is where I kind of like, there's so many ways to thread this. Like, I'm not sure exactly how this shakes out, right? Like how interesting versus trivial the answer ends up being. So, so let me think of a few answers. So I think there's kind of there's kind of like different ways, different levels of description, different kinds of mechanisms we might pull out of this that could explain the behavior we're seeing. And some of them are kind of deeply uninteresting. And one problem I have with language models in general is that like they have this very strong inductive bias, which is like operations over meaningful tokens, right? So it's like, yes, by giving them text, in particular text used meaningfully by people on the internet, like you've given them a huge starting point to the kind of symbol discovery problem, right? Like a lot of work in the early debates are like, where do concepts come from? And for an LLM, you're basically like, here's the vocab of concepts, and I'm going to give you data that shows you with really high signal which concepts are similar and different and stuff. So if that's a lot of the problem, then that's, I don't think we'll get headway on answering that with LLMs. But there's other kinds of types of concepts and algorithms, like maybe like some of the other things I'll talk about that could be informative and interesting here. So one of the things I was saying, like with these kinds of behavioral studies, like this first project, I kind of think of like when, as we were working on the project and similar projects, they're like deeply necessary. Like for this program to be interesting, we need models to be empirically in the running, right? Like it's not worth asking, is the LLM human-like if it's not, or is it does it propose a new theory if it's bad at the task? So you just have to start by saying, does it have good predictive power? At the same time, you can conclude basically zero from that, right? So it has this like really empty feeling too of being like, look, the LLM is matching human behavior in this way. And like so many people get like, including myself, are like, eye roll, like I didn't learn anything. Like LLMs are good at so many things. Telling me it's good at one more thing is not deeply interesting. But there's no way around, like you're not going to bother, like there's a reason we didn't ask how human-like are, these neural networks that they just completely flop, right? So I think these behavioral tests are like an absolutely essential first step. And at the same time, like tell us very little. There's just basically permission to continue down this path rather than saying much interesting. Cool. Right. Yeah. And I would say for these other, like when I talk to people who are working on these other problems, like everyone has this same feeling of like, okay, check the LLM is good at the behavior, and now what is the mechanism? Is it interesting? And that's where everyone's going next. Yeah. So at that point, I'll talk to speak to one type of mechanism or thing we might think about here that's maybe, more transparent just from the structure of LLMs, but I think deserves kind of attention. Like this is the kind of thing like, I'm like, is this obvious? It wasn't obvious to me, but maybe it's obvious to other people, this kind of relationship in context and in weights learning. So I'll talk to this. This is a bit of the system 1, system 2 issue. So again, so the point is, when we're thinking about this kind of need for hybrid systems and neural symbolic systems, the kind of argument goes, well, human learning is not one type of thing. So this is just my thinly veiled attempt to get a video of my daughter in because she's so cute. Look at her. So here she is learning how to use a cup, and she's not very good at it, and she's just kind of chewing on it. And this is a type of learning that that kids do a lot, right? So before she learns how to use a cup, she will have like tons of interaction with a cup. I mean, now she can use a cup. She's much older now, but lots of interactions with a cup of this type, and very slowly over time, she will eventually learn the exact way to pick it up and hold it. And there's no water in it now. I think it had already spilled at this point, but so it doesn't spill water and things like that, right? And then at the same time, there's other kinds of things like you go to your friend's house and you're just helping unload the dishwasher, and you require absolutely no previous experience with this kitchen to decide where the cups go, right? Because you can kind of quickly grok it and you can see what the patterns are, and you can be like, I'm going to put the colorful mugs here and the wine glasses here and whatever. And so the point is like, these are very different types of behaviors, and there's absolutely no reason to think, and they're going to be very difficult to model with the same system because they're just very different types of things, even though in some ways we would call both of them kind of learning or reasoning in some context. And so there's this kind of notion of these dual systems, right, where we have different types of systems that are explaining different kinds of behaviors. And it's funny that the question is about system 1, system 2, because I've given a version of this and I've called them system 1, system 2, and I've gotten people who don't like that terminology. And so I was like, I'll just make it blue and orange. And somehow this absolves me of making any theoretical commitments. I think it's uncontroversial to say, hey, there's kind of clusters of things that are considered to hang together. There's types of learning that are slow and incremental, they're habitual, and they're highly retained, like learning how to ride a bike, learning how to play piano, learning how to drink from a cup. And then there are things that are fast and kind of flexible and adapt well to new situations. These are often thought to be kind of rule-based and compositional, right? So learning how to ride a bike, not highly rule-based. It's hard to articulate that. Deciding where to put the cups on the shelf, pretty easy to verbalize in articulatable rules. These things are also not very well retained, right? You'll forget them quickly once you're maybe doing it largely in working memory or kind of short-term memory. You're not going to remember where you put the cup like decades later. So like I said, this is on this place of like many ways to thread the needle. I've gotten pushback with this. I wanted to like shout out to Ulrike Han when I gave an earlier version of this talk, and she gave like really good thoughts about this issue. And so I was considering getting rid of this kind of dual systems framing because a lot of people don't like it and it made me feel like I didn't know much about, and I admit like I'm not an expert in this. But she was kind of sympathetic and saying like, I think part of what this work I want to talk about is dealing with is that the dual systems view is like correlated with, but not exactly what we want for human cognition. And I think that's kind of what we're going to see in LLM. So I kind of want to make this point that there's something to this. There's obviously these kind of families of things that hang together, but it's not quite two systems. And so some of the tension goes there. So I just wanted to shout out to Ulrike for kind of having nice thoughts on this, which if you want to talk to someone about. So I'm going to stick with this idea of kind of a blue system and orange system. Conveniently, the first one and the second one. One might call it 1 and 2. And part of the issue in kind of traditional models, this kind of traditional narrative, is that there's been a lot of criticisms of neural networks in symbolic context because neural networks are always taken as models of the slow incremental type of learning. So some papers that I've really liked, very influential to me, say like Brendan Lake and Marco Baroni, Najong Kim and Tal Linzen, that kind of have these examples of neural networks failing at compositional generalization, for example, because you train them on these things and they just do a very bad job going outside of their training distribution. Even if they've seen all these words, if you recombine them in different ways, they're confused, right? They know what a red triangle and a blue square is, but they can't do a blue triangle. But again, the problem is like, this is kind of simple neural networks. And now we're looking at neural networks that can seem to exhibit this kind of fast in context learning. And in that case, they do seem to be doing things like compositional generalization. So this, again, kind of showing the analogical reasoning task from Taylor Webb's work, which I think nicely illustrate this. And so the kind of claim here is that when you have this in context and in weights learning within a single neural network, this gets rid of the need for two distinct systems, because these two things are kind of can explain both sets of behaviors in an elegant way while still being kind of two faces of the same system, right? So we typically think of like this, the cartoon of the neural network, and you have your weights and you have your activations. And so I kind of like this view of it, because to me, it's like this two sides of the same coin thing. So you kind of, it's one neural network, but you can think about the weights or you can think about the activations. And these things are obviously intimately connected, right? The weights produce the patterns of activation in a given context. And then these patterns of activation yield some kind of behavior, and that accrues some reward or some loss. And then based on that reward or loss, you go back and you update the weights in order to change the activations, et cetera. This is the in-weights learning. But over time, you will start to get patterns that are very systematic and can be solved in activation space, because the weights will yield a pattern of activations that is very responsive to the context. And so you will just get things right and you will not accrue any loss. And this will start to look like doing in-context learning. You're going to get the prediction correct. You're going to recognize the pattern, but you're not going to make any updates to the weights as a result. And so you can figure out these patterns in activation space, and now you don't need to update the weights. And so you can think of this as kind of these having the properties of these two systems we're looking for. These weights are going to be updated slowly and incrementally, and they're going to have very high, right? It's really hard to unlearn stuff in weight space. Whereas if you can solve stuff in activation space, it's going to look a lot like that system too, because it's fast and it's flexible and it's not going to be at all retained. There's no in-weights updates here. And so what we wanted to do is look at some results from the cognitive science literature to show that if we have a neural network that has both in context and in-weights learning, it kind of naturally subsumes the kinds of behaviors that we're looking for, where the in-weights learning takes over in exactly the cases where you would want it to and shows the behaviors that you want it to, and the in-context learning, the opposite. So I'll just show some of the results because there were a few different studies in here and it gets a little cumbersome to go through all of them. So here we're looking at a compositional generalization task from Decker et al. So what this task was people were learning to place colored animals on a grid. And so you would be showing them examples of like one at a time, showing examples, like flashing them on a grid, and then you would get a new animal and you would have to say where it goes. And so in this case, if you were to show, for example, you can imagine I should have animated this, but I didn't have time, didn't think to until now. I'll do that for the next version. Like if you imagine you got like the column first, so you see all these yellow animals go down the column, and then you see all these fish go along the row, one color at a time, and then you're asked where the blue owl goes, you might infer that it goes up here, up in the top left, because you're like, well, it seems that columns are corresponding to colors and rows are corresponding to animals. Whereas if you get the same amount of information, as in you get just as many rows and columns, like just as many individual points revealed, and you cover all the rows and all the columns, this is what we call call this blocked and call this interleaved. Then this is actually much harder for humans. And so what this paper showed was that you get, people can do the compositional generalization, like having seen yellow owl and blue fish, they can infer blue owl when they get the blocked curriculum, but when they get this interleaved, they do a bad job at that generalization. And so the kind of takeaway here, and as well in some of the other studies that I'm not showing kind of for time, is that there's this kind of rule-based system that prefers this kind of block curriculum, and it can generalize compositionally. And this is in contrast to this more incremental system, which responds when there's not rule-like structure, and then it likes to see this shuffled interleaved curriculum. And so what we're going to do is we're going to meta train a neural network on this kind of a task and try to show these patterns. So here we have an individual task instance is like a grid with a set of animals and attributes, say, and a single held out one that needs to be placed on the grid. So like it would get this task in context in text, where you would be given, what was it, 9 kind of adjective, noun, location type things, and you would be predicting the 10th one. And during the meta training, so the weights are updated over many such grids with different combinations of symbols and attributes in different locations. So you're going to meta train in order to solve an arbitrary new grid in context. And then we're going to look for the kind of differing properties of the in context and in weights. So first, kind of as a sanity check, you could say, imagine you don't do the meta training. So you're just going to train a neural network on a single grid, you know, or yeah, I think just a single grid, update the weights, and then test whether it can generalize to a new grid. And in this case, it does a terrible job. So first, it prefers the kind of interleaving in order to even solve this single grid, kind of for a held out thing. And it forms plurally when you block the data, and it can't generalize at all to a held out task. And this is consistent with the kind of traditional view of neural networks. If you have only in-weight learning, if you block the data, you'll get catastrophic forgetting, and you're not going to generalize well because you're not really encoding structure of the task. So this is kind of sanity check that the in-weights system kind of behaves as expected. Then when we meta train the system so that it has in context learning, then you can see it does, it can solve new tasks in context, and but in particular, it really prefers that blocking advantage, right? So here we have this kind of rule-based system that likes to see, that can solve new tasks in context, but in this case, it, just like in the human case, it benefits when the rule is made very explicit by showing like the row and then the column. If you provide shuffled examples, it actually has a hard time inferring the rule here. And then we have this kind of additional condition, which is the importance of the rule-like structure in invoking the in-context learning system. And I think this is a pretty important one. So in this case, we have this this grid that looks like this, and here it's like axis aligned. So we'll call this, and this is using work from this other paper that I'm again not showing for time, this know-it-all paper. We would call this a verbalizable rule. Like I could easily say in English, animals are on the rows, colors are on the columns. Like it's an easy to understand rule. And in the kind of cases, your rule-based system that likes blocking takes over when such rules are easily verbalizable. They're kind of transparent and readily available to you. What you can do is you could rotate this grid. So now it's actually pretty hard to articulate what the rule is here. And now this breaks your ability for your rule-based system to take over, and you fall back to the in-weights learning. And we see that that's exactly what happens. So if we try to give it this rotated grid, now it can't zero-shot generalize anymore. It has to start updating its weights, and then it reverts to having the interleaving advantage. This is text-based, and this is so it's literally just like coordinates, but we've meta-trained it with that orientation. So this is awkward for it, right? So it's kind of, you could also meta-train it with this, and then that would break the rule. So it's kind of like if you get something that's not verbalizable within your concept space. Yeah. So this, yeah, go ahead.
Related to that. So when you provide text description, you're providing a coordinate. And I assume you're providing them in order, like rows, columns, and there's some order.
Yeah, yeah.
What happens if you permute for the block one, if you permute the order of the rows? Does it still get the block advantage?
So like within an in context example, it's not consistent which is a row and which is a column?
Like, depends on how you're,
That,
you know, if it's row 5, 8 to E,
Yeah.
still going into the permute. So you provide the same information, but the order of the columns is permuted.
I would have to double check, but I think that's what is done. So I think it's actually like the same set of examples, and it's just a matter of how they're ordered, right? So it's actually like, and I think this is kind of, it's interesting like that. It's basically like, because these things are all together, like you see yellow owl, 1, 1, yellow butterfly or fly, 1, 2, yellow, like you see all of those together. It's easy to pull out the relationship between yellow and that thing. If you shuffle them, it's just more work, and it just struggles more.
Yeah, so if it's visual, that's clear, right? Like in the blocks version.
Yeah.
It seems like it's something visual.
Yeah.
Line. And I bet that if for a human, you permute the role, so you presented the information in a way that you can just do visuals.
Yeah.
But it's interesting if the model doesn't have it.
Yeah.
Don't use the visual.
Yeah. So there, yeah. So 2 answers. So in the one case, we kind of, it's a little tricky because we meta trained it with this structure. So it's learned to, like, if it's meta-trained on blocked examples, it can learn that that structure is common, and therefore it's kind of assumed that it will have this local structure in the training examples. So then when you, so there's a little bit, but I will say, it's in the back of the slide, but like when we train LLMs, which we obviously didn't meta-train, they show the blocking advantage pretty strongly. So that at least suggests that something about the structure of natural language also invokes this kind of assumption of locality, which I think is pretty reasonable. So I think even in text, like for humans, this kind of visual locality seems quite salient, but I think even in text, there's this kind of locality bias that you would kind of assume relevant information will be grouped together. That definitely influences LLMs. I agree it would be harder for humans, but in the text form, but I wouldn't be surprised if they still preferred to see, like, if I saw a list of all the words and all the numbers, like it would be still kind of visual, easy to pull that out. But yeah, that'd be worth, yeah.
Yeah, so how would the framework be updated for including the reasoning models responses? Because if like the slow learning is happening in context, then what's happening in the weights?
Sorry, so the slow, you mean in the reasoning model, the slow learning is happening in context? Yeah, so slow maybe isn't the right distinction here, or the right word, or at least slow is like like a multi-meaning word, right? So there's like slow as in, like the slow in weights learning means like you need exposure to many, many examples and lots of small updates, like learning how to ride a bike. But I think the slowness of the reasoning models is like you're thinking a long time about it. So maybe the better thing is like explicit versus implicit learning or something, right? So in the in-weights models, I would still say this is very much part of the rule-based system. It's just you're taking longer to do it. But I will say, this is I think a deep question that I've been very interested in is like what analogies we make between what is happening in the LLM or any of these systems and what's happening in the human, because there's, analogies are weird. There's no ground truth analogy. And like the way we make the analogies really affects how we build the models, how we understand them. We were talking a bit about this on like the reasoning models specifically. It's like, to me, when I see like a chain of thought reasoning chain in an LLM, it could be analogous to any number of processes in a human. One is taking a longer time to think. One is penciling, papering it out. One is verbalizing it, right? And those probably all have different cognitive neurological effects. So just taking a longer time to think, but not writing it down allows you to solve some tasks better, but not other tasks better. Sometimes you need to externalize it so you can refer back to it. In an LLM, chain of thought both gives you more time. You literally spend more compute, but it also externalizes stuff that you can go refer back to later. I think those are like multiple different processes happening together. And so it's kind of interesting to make these analogies because it might, like, we might be overloading a process that should be different processes and there might be trade-offs there. Maybe we could do it more efficiently. Like, I think there's something there. Yeah. Cool. Yeah, so the takeaway here is basically that you have these processes, you have the in context and you have the in weights. And the in context is dominating when there's rule-like structure. And when there's rule-like structure, it likes to see, for example, blocked rule-like data. When there's not rule-like structure, in context learning fails, falls back to in weights learning, and then it behaves like a traditional neural network. And the thing that's so nice about this way of thinking about things is this happens quite naturally. It just like happens as a consequence of the way that these models work. So it's kind of two systems, but it's also kind of one system that's just doing what it naturally does. Again, I think this is hardly the only paper point, and I think one of the kind of, there's this other work that talks about kind of meta-trained neural networks, specifically being really useful as models of human cognition, and that you can, in this kind of meta-training, you can have a system that kind of transcends or overcomes the kind of traditional properties of the neural network, right? So the in-weights learning can then give rise to a system that doesn't have the same properties as the underlying learning system. So I think the kind of summary takeaway of this piece is that humans exhibit very diverse types of behavior depending on the context, and so do neural networks. So what might have first seemed like two systems maybe is better captured by kind of two faces of the same system. And then properties that were once described to the symbolic components in something like a neural symbolic system might actually be explained by in-context reasoning versus explaining the other ones. So again, this kind of, kind of one system kind of subsuming these things. got a lot of questions, but I'll pause again.
The slide where you're showing the parse.
Right, it did. That's correct, yeah.
Do you think it would work better if you like, explicitly model give you a rotated grid rotated by 47? It's going like explicitly it would be able to say top row.
Yeah. Yeah, so again, so these were like meta trained just on this task, so they're not LLMs, so it would have absolutely no idea what to do with the instruction. Yeah, the LLMs don't have complete zero shot. I forget, maybe I can find the slide on the LLMs. It's not a nice figure because I just copied it from an old version of the paper, but it was something like this. So I hated these figures, so it takes me a second to look at it. But so it'd be like the rule like, so in the rotated condition, yeah, so GPT was actually pretty close to zero, although we didn't prompt it in this way. But like Llama 2 was doing not zero, you know, like it had some signal, but it, you know, it wasn't convincing. But yeah, we didn't try prompting a lot, and we didn't try, and I forget which GPT this is. I think 4. No, I don't know. But yeah, like so we probably could try prompting and things like that. And that could affect, although it would change. Like if I'm interested in this case in the kind of mechanism, I don't know what I would do with the information that the instruction improved it. Like for this particular question, I don't know. I'd have to think about what that would mean for the in context and weights trade-off, right? But it would be something like the instruction is a rule, verbalizable rule that invokes system 2 and maybe forces it to use system 2 in a way that it otherwise wouldn't. Be really interesting, but I'm not entirely sure yet. Well, any other questions about this part before I jump into this last? All right, so the last piece of this is structured representations. And I actually say this is probably the part where I've spent the most amount of time recently. Like a lot of students in my labs are working on various aspects of this because I've gotten very excited about the fact that we might even consider neural networks as having structured representations. So I think there's many ways to make this argument, and I wanted to kind of provide 2 flavors of kind of very different types of structured representations that you might pull out of a network, but that I think still speak to the same general problem here. So I'm kind of organizing these as like there's kind of structure in concept space, which is or like structure in kind of algorithmic space. And these are kind of both in play in the same networks, but they have kind of different flavors. They feel like they're speaking about different types of things. Sometimes I kind of think of this as semantic and syntactic, but I don't know if that's the right terminology here. So I don't know. There's 2 kind of flavors of mechanisms to speak about, and I'll talk about both of them. So this first was a project where we're kind of looking at the kind of the decomposition of concepts within the network and how structured these might be. And this is in a fairly architecture neutral kind of a way of thinking about it. So here we have a vision task, and it's an odd one out task. So here the model is supposed to predict that this one is the odd one out. And we have, you know, this, if you're thinking about it, hopefully you're recognizing that there's kind of 2 features here. There's like insideness feature and an in contact feature. And this one is neither inside nor in contact. And so it's the odd one out. And so there's kind of 2 possibilities for how the model can solve it. One is the kind of traditional thing that neural networks are assumed to do, which is to learn idiomatic kinds of representations, so that you would kind of just learn like a prototype or a template for each way that these features could combine. And you would do some kind of matching and say which one is the most distant. And then the other is to actually learn the features and kind of place concepts along these different features such that you would say, you know, these 2 groups are similar in their insideness, but different in their contact. And these are different in their insideness and similar in their contact. And so we want to find evidence for this latter because this is what we would call a structured representation, or what we were calling in this paper structural compositionality, this idea that the model kind of explicitly represents the composition of 2 features within the more abstract class. And so what we were working on here is trying to find what we would call subnetworks that correspond to these specific features. So what we would want to see is like within our little neural network, there's some subset of the weights that are kind of computing whether insideness is true, and some other subset that is computing whether contact is true. And we could be able to isolate both of these and kind of turn them on and off in the expected way. So we're using a method called continuous sparsification. It's basically you have to learn a mask over all the weights of the network, given some examples of insideness and of contact, and say like mask out as many weights as possible while still retaining the ability to recognize the insideness classification. This has been used for like model pruning and things like that. And so we find what we would like to see is that if we found kind of an insideness subnetwork here, it should perform well on finding the odd one out when the difference hinges on the insideness feature. So like in this case, but it should perform poorly when the odd one out differs along the contact feature. And so we take the difference between these two cases and we want to see a positive difference. And this is when we're using only the subnetwork to do the classification. So we kind of mask out everything else except the subnetwork and do the classification just based on the subnetwork. And what we should see is like points that are like in this top right corner, and that would show that it's performing well when it's supposed to, and it's not performing well when it's not supposed to. And then we do this kind of inversion piece of it, which is that we ablate this subnetwork and use the remaining parts to do the same classifications. And here's where we want to see the opposite. So this kind of blue region is testing that the subnetwork indeed captures the feature it's supposed to capture and not the other stuff. And then this bottom right corner points down here means that the information about that feature is kind of contained within that subnetwork such that if you delete it, that information doesn't exist elsewhere in the network as well. So kind of a success is that we should see points in the top left and in the bottom right in these cases. And so here's what we look at. We look at results across several different kind of slight variants of these vision tasks and also these some language tasks, so vision and language models. And across the board, we see pretty clean patterns kind of consistent with this. There's a few failures. So if you're wondering what like a failure looks like, it's actually this one, like in a randomly initialized network. This isn't a randomly initialized network, but this is a failure case where like what we would see is like even in a random network, you can usually find a subnetwork that does the thing you want. But when you ablate that subnetwork, it does not have the desired effect. So that's kind of what you see in this case. But for the most part, we don't see that. Like for the most part, we actually see pretty strong expected effects of the ablation. So this is kind of evidence that across these different features or tasks and models, we're getting these kind of separable features that you can isolate the insideness feature and the contact feature, and you can kind of turn them on and off without grossly affecting the other one. We did some follow-up work that I think was nice to put this in context, which is that these features, because this is a very simple, this odd one out task is kind of very constrained, but it's more that if we want these structured representations, they should behave the right way in kind of more abstract computations as well. So here we looked at this same different task. So you can do a kind of basic discrimination task where you get two objects and you have to say, are they the same or are they different? But you can also do a more abstract task, and this gets used in cognitive science as more abstract definition of same versus different, which is called relational match to sample. And basically it's saying, is the relationship in the left-hand side the same as in the right-hand side? So if in this case on the there's two pairs of symbols in each panel, right? So this would be same because these are different and these are also different. And this would be different because these are the same, but these are different, right? So it's like a one level up abstraction. And so what we're going to do here is use similarly, like try to find these isolatable subnetworks that correspond to, in this case, the shape and the color of the image. And what we want to see is if you can ablate out or swap the features, if it's going to change the predictions in the same different and in this relational match to sample in the expected way. So what we can do is have some kind of some example here where we have, in this case, this is different and this is different. But you could say, I'm going to like replace this shape with this other shape by making an edit internally in the weights of the model, not in the input, but like to the subnetwork. Or I'm going to replace this color with this other color, again, by editing this subnetwork and see if it changes the prediction. And so this is showing for various models the layer at which you make the intervention. And the point to take away here is that these bars are very high, close to 1, in a particular region of the model. So what this is showing is that there's actually a quite good representation of these discrete features of shape and color, and that you can edit them early on in the network and then change the subsequent predictions about same versus different, and even in this very abstract case. But you'll notice that you can't actually change those things too late on in the network. Like at this point, the model has already encoded and is doing some later operations on the symbolic representations. And so like editing the feature, the color feature later on is like you've missed your window wherein this is relevant. So this is nice evidence that these structured representations of the features are not just like playing the kind of having the correct functional role in this trivial case, but also in these more kind of abstract reasoning problems as we would like them to in these more compositional systems. Cool. I can do a quick pause there before I give a different kind of flavor of structured representation story. Cool. So there's like a different way that we might see these kind of structured representations playing out. And this is probably more familiar if people work on mechanistic interpretability, which is, you know, all the rage these days. So here, so this is less about the kind of, like I said, what I would call the semantic features of the input, like what is the color and the shape and are those separable, and more about like what are the operations that the model is running over the inputs that it receives. And this is also a really key part of these what we call symbolic systems, right? Is that they're like operating in a kind of content independent way. And so there's been a lot of work recently on these kinds of what we call circuits. So kind of what I think of as like the go-to circuit that's become like widely studied and I'll show in a second reproduced is what's called this IOI circuit. So this is from work out of Berkeley from Wang et al. And they were studying this, what does the model do when it has a task like Matthew and Robert had a lot of fun at school. Robert gave a ring to blank, it needs to predict Matthew here. And they find a sequence of attention heads that basically runs a very simple but easy to interpret algorithm, which is that first there's a head that flags the duplicated name. It says Robert appears twice here. Then there's a head that blocks attention to the duplicate. And then there's a head that basically copies whatever names haven't been blocked, right? So this is a really stupid way to solve this task. So quite a nice little algorithm, right? It's like stupid in a linguistic sense, but it's actually quite smart in an algorithmic sense as in its kind of clear, you know, like kind of symbolic-y in a certain way. So we have these kind of discrete components that are doing things like detecting duplicates, blocking attention, copying, right? And so the question from this kind of symbolic system standpoint is like, are these things modular, general, content independent, reusable? Because that's the kind of properties that we often think of as being necessary in this kind of what we would call structured representation. And so in one project follow-up, we were looking at a different task. And then this one, this is what we call the colored object task. And it says like a list of objects on a table with colors. And then you just need to say what color is a certain one of the objects. So it's on its surface a pretty different task. Like if I were to think of like the language processing pipeline or something, it's different. But what we actually find is it in the first, just like when we look at how it's being solved, if we use the same model that we just used on that IOI task, it's actually using identical components for a lot of this. So it uses the exact same duplication or duplicate token heads to identify the duplicates. Then instead of this inhibition, it has something we call a content gatherer head, which is a word borrowed from a previous paper. And instead of blocking, this kind of promotes attention. I'll come back to that in a second. And then it uses the exact same copy head to copy over the nouns. So there's this kind of interesting picture where kind of 2 out of 3 steps are exactly shared between these two tasks that are on their surface pretty different. But then when we kind of think about the kind of modularity and content independence, something that's worth pointing out is the model is very good at IOI. It always predicts the right name. And it's actually very terrible at colored objects. This is like GPT-2 medium or some tiny model. And so it's basically at chance at picking the color of the object. It just randomly chooses between the colors that are named. And I can go into details later, but basically we're saying, why isn't it using its inhibition here? Because inhibition was critical for avoiding the kind of chance between the 2 names and the other one. So you can kind of go in and rewire and say, route the attention of the inhibition head accordingly. And if you do that, you can perfectly recover this performance. So it's, again, making this point that these components are kind of modular and they're not so content specific that you can't just invoke them in a context where they weren't being invoked, or that you can invoke them in a context where they weren't being invoked, and they will behave in the expected way. Again, I think of this very similar to what we would think of as like calling a function in a piece of code, right? Like it can operate on certain inputs, and you can kind of mix and match them in that way. We also have a recent paper where we showed the same circuit reproduces even on multilingual models and even on monolingual Chinese models, which I think is very interesting. So in this case, we were looking at the QN model, and which didn't have any English text in its training, as well as on multilingual models like Bloom. And we find almost identical circuits with some interesting differences that appear to correspond to linguistic differences, like the need to inflect verbs and things like that. So there does seem to be something quite consistent and reproducible about these kinds of components, which suggests something other than kind of idiosyncratic associations going on. Again, I think there's a ton of work. These are all kind of older papers, but from people who I think are doing really good work in this area. But I just didn't feel like updating this slide with callouts. But there's tons of work on these kinds of mechanisms in models. And so I think the point here, kind of sub-point before zooming back out, is that the fact that neural networks succeed on these kind of so-called symbolic tasks is sometimes construed as evidence that they don't need symbolic structure, right? We think of neural nets as like the antithesis of symbolic structure because they're just these loose webs of associations and points in space. But I think this is just flat out a wrong conclusion. Like if we're looking under the hood at what's happening in the neural networks, it's at least correlated that as they're getting better at these symbolic tasks, the representations are also acquiring a lot of the properties that we've traditionally thought were part of symbolic systems. Like I said, I think this Quilty Dunn paper is nice and a good read, and he's talking about a lot of other stuff with this language of thought hypothesis specifically, but he does make this point about these, what I call the kind of syndrome property, the fact that there's these properties that we tend to ascribe to symbolic systems, and just he's talking about in animal and human cognition and development, but they seem to cluster together. It seems to be the case that when you get compositional generalization, you also get filler role independence, you also get logical structure, you also get things like predicate argument structure, you also get things like structured representations. These kinds of things, it's hard to say which ones cause the other ones, but they do seem to hang together in a way that doesn't make sense to explain by chance. I think there's something really there to the fact that neural networks seem to be obeying the same property, right? And I think it's kind of something interesting worth following up, and does kind of push against this dichotomy between neural networks and symbolic systems. I think it's a nice invitation to refine some of these theories. All right, so I'll wrap up with a quick general discussion, which I think I've been making the points throughout. So when we talk about neural networks today and like what's different about neural networks today, there's usually an emphasis on scale, but I think there's a pretty important, at least apparent change in kind, right? They're doing a lot of things that when we think of neural networks and the way we've talked about neural networks in the past, we're just kind of categorically, almost definitionally not what neural networks do. And now those neural networks seem to be doing these kinds of things. And this is across a range of types of studies. So when we look at their behavior, they're behaving in ways that we used to think required symbolic structure. When we look at how they learn, they're learning in ways that are not just the traditional in-weights learning, but they're doing other kinds of learning. And when we look at their representations, the representations are not just this like globby glue of associations, but they seem to have this kind of structures that doesn't really represent nicely as like nodes and edges or points in space. Not only as those things, that obviously also can be represented as those things. So one place where I feel like the debate is often lacking these days is there's this, we kind of cheapen it, right? We kind of assume that the implications are simpler than they are. We either say that because neural networks are succeeding, this is like a wholesale rejection of everything we've thought in cognitive science, that clearly it's all just empirical and there's no need for the structure. And I think that's a massive oversimplification of what's going on. But there's also this kind of tendency to want to dismiss them and say like, well, we don't know what's happening under the hood. It's probably all tricks. It's mere illusion, or they're stochastic parrots, or these kinds of things. And that's also not a fair sell of what we're doing. I had some kind of opinion paper there with philosopher Sam McGrath, who did a nice job writing it up, and Roman Feynman and Jake. So that was just a citation of that. So I don't know. This is where I wish I had, and I think maybe, I don't know, 1 year, 5 year, 10 years, someday there will be a slide that's like, here's the grand new theory and this is what we have. Right now, I think my only takeaway is like this kind of like patience and persistence feeling of like, I just can't see how we get to the end of trying to study how LLMs work and we haven't learned something very important about how intelligence works and how the mind works and how cognition works and how language works. But I think that we will lose the opportunity if we like try to know right now, right? Like if we just like try to be like, I know what the answer is, it's definitely this and the problem is this. And so kind of focusing on what is happening and why within the LLM, I think is exactly the right question. And I just feel like if we answer that well, then in a couple years or sooner, it will become apparent what it means, right? So that's what I'm excited about. And that's what I think there's a lot of opportunity for. And there's some references and thank you.
Yeah, so this is probably David's question about distinguishing between something in the circuit and like the mechanism. But like, have you looked at problems where you need chain of thought to solve them? Because that is a case where the computation really is different. You just take it face value, the chain of thought is important. If you remove it, and you get different answers.
Yeah, like we are looking at it. I would like, have we looked at it? Not as much, but we are looking at it. So Jay Cruson is a postdoc who's been really interested in chain of thought. I do think I definitely think this is fruitful. I might push back on saying like the mechanism is different in the similar way as like kind of the system 1, system 2. Like I think there's kind of a direct trade-off between these things. So like you can imagine there's being certain things that like maybe are solved with chain of thought in some contexts, but overtraining might get pushed in weights or be solvable earlier with less chaining, right? Like there's kind of probably more continuity between these types of learning and reasoning than we allow right now with the models, because we like freeze them and then they can only chain of thought or in context learn, which isn't really if you think about human learning, there's not like this, like you've pre-trained and now you're frozen and all you can do is in context and chain of thought, right? So I think if we like freed that up a bit, we would see more fluidity between those and that would be quite informative. But I do think right now there's probably a lot to learn from looking at the models, the ones that can be solved only with chain of thought. So what Jake has been looking at is analogy problems and problems where you get it wrong without chain of thought and in which kind of context don't you. We don't have a great answer yet, but yeah, I agree that there's probably insight to get for that. Did you have a particular?
No, just how to think about it. Because that's sort of a different, slightly different than this access we had before, like in context in ways.
Right. Totally. Yeah, totally. I think there's like, not only is there probably not 2 systems, but there's probably much more than 2 systems, right? Like there's a lot of things going on. I do think something I'm excited about and we've been talking about is just the artificiality of kind of segmenting these things, because again, in a person, you would imagine like when you solve a task in context, it feeds back on your weights in certain ways. So like I'm working with the colleagues in neuroscience who do a lot with working memory. And there is this kind of, trade-off where like if you have to have very high effort working memory constraints, you can retain that better, right? So it'll take longer, it's more work, you'll have more errors and things up front, but then it will be retained better. And so you could imagine something like the chain of thought actually having an effect here if it were able to feed back on the weights in the certain. So yeah, I think these, like drawing the lines between these is probably limits and the reality of how they should work. And yeah, there's probably way more than. Thanks. I guess back there.
So fascinating talk. I always struggle with LLMs about what's on the training set, what's on the test set. Are the tasks that we test on really different from what is? And I think you alluded to some of your reservations and maybe the English, Chinese stuff speaks to that. But I wonder what you think about this. How much are we doing cross validation? How different are our tasks from what's on the training set?
Yeah, I think it depends on the question you're trying to ask, right? So for some types of things, so I'm trying to think about the work I studied here. So like in the first one, definitely data contamination would be a problem if it had seen that task before, right? Like if it's seen these things. Does seem unlikely because we made the text version of the task and, you know, but it's possible it could have seen something like this. But it also performed poorly without the tuning. And so like there is some possible risk of data contamination in that one, I would say. And that's also where I kind of say for these kind of basic behavioral studies, you're like, they're kind of a permission to continue. They're not much, so like it's basically, okay, it's performing competitively. We should therefore now continue to ask ourselves how. And it's possible that on further investigation into the mechanism, you're like, oh crap, it's looking up the Wikipedia posts that describe this task and it's using an induction header and retrieving the answer. Seems unlikely, but like could happen, right? So that's a possibility and it's not ruled out by the success. The other ones, like for the, you know, that's why sometimes we do meta training toy networks. Like you kind of use the LLM as an inspiration about the mechanism, but then you go and replicate it in a smaller model where you can control it, right? And I think a lot of the really useful work to happen on cognition and mechanisms probably requires that. Like you can use the LLM as a source of inspiration for what the mechanism might look like, but the LLM itself can't be the inspiration and the test and the conclusion, right? Like it needs to, like you need to get outside the LLM, right? So if it's serving as a model, it should be a model, and then you need to like get stuff out of the model and go test it. So I think that's kind of my general answer to this is like LLMs have these problems. They're never going to not have these problems. And instead of fixing it by trying to like get really bizarre about how held out your data is, it's more like your theory should be mutually supported by many independent types of experiments, which have different uncorrelated sources of problems, right? There's kind of typical science story.
Thank you for the great talk. I was really interested when you were talking a little bit about how we don't yet have a definition for what like symbolic or classical types of computation are. But I think like potentially we could draw from some of the sources that you had on that really nice overview slide. And I think some of those include things like structured representation as opposed to like featural decomposition, and also include things such as rules that are sensitive to those symbolic structures. And I just thought it was interesting that the work that you highlighted doesn't really necessarily draw from the like sort of classical conception. Like modularity, say, is part of like the classical conception, but those are like independent.
Yeah, totally. Yeah, so I like this. I try to think a lot about like what would count as symbolic. The definition of a symbol. I actually feel like I spent a lot of more time than I should have thinking about. No, not enough time thinking about it. I don't know. But so my feeling for saying we don't have a definition is there is really formative work that tries to lay out very clearly. So I think of Jerry Fodor does a lot of this. Barry Marcus, like the Simon and Newell symbol systems, like there's really classical work on like what is a symbolic system. And the problem with it is they act like they're describing a theory, and what they're doing is describing a particular thing, which is something like a Lisp program that does it. So it's easy to describe an artifact as though it's a theory. And now we have another thing that is not that artifact. So it's like, to me, when I read Fodor, it's like the test of being a symbol system is it the program he is currently describing? That's not a useful theory, right? And so we're now being challenged on what is a symbolic system, because we have another thing that seems to do a lot of the stuff we thought we wanted symbolic systems for, but doesn't fit this description. And that's exactly pushing the definition. So I like the Quilty Dunn thing because it's a really modern update of like this kind of Fodorian arguments that seems to grapple with this better and kind of admits that like this, these things exist on a continuum. We have these unambiguously symbolic systems like a Lisp program, but then we have other things that are going to be more or less symbolic, and maybe it's not a cut and dry set of criteria. Definitely when we're talking about the human mind, it's not a Lisp program, right? It's just objectively not. So we need some criteria that would allow us to say is it symbolic or not that aren't those tests. So I think that's part of the problem. I think there's a similar discussion that's going to come up with a lot of discussions around words like intelligence and understanding, because I think the same property is kind of true where when we define those things, we really were just talking about humans. And so we never had to define them in a way that contrasted them usefully with another existing system. It's not as much the case because there's animals and there's various other things, but like I think this like redefinition is like exactly how this theory moves forward. It's like we realized we were using words that we didn't really know what they meant, and then we'll redefine them, and that's kind of the evidence of theoretical progress. Back there, I think.
Thanks for the talk. So most of the tasks that you presented are non-linguistic nature, grids, images, and so on. But yet you use mostly LLMs, so largely trained on text. And you said something that was like interesting that I like, because you give LLMs basically a vocab of concepts through text, right? And I'm curious in your thoughts on how much do you think that matters? That the fact that we give them these like text concepts, or just like any other structured data and biological.
Yeah, I feel like it matters a lot. Like this bothers me with LLM. Again, it always depends on what question you want to answer. So like for the work we've done so far, I've been so excited. I feel like a lot of this stuff has been, to me, justification of continuing to work on this stuff. So it's like proof of concept. A neural network can learn a content independent function like a duplicate detector. Cool, check the box that it is possible to do this kind of thing. Cool, proof of concept, the model can learn these decomposable things. But then the questions that I would consider myself really deeply interested in are like, what is the structure of language in your head, which includes the inventory of concepts in your head, which is like, what is the structure of those concepts? And I'm like, there's this like thing lurking in the future, which is like, I think the LLM fundamentally can't answer that because we gave it the concepts. Now, granted, there are some people who say this is where like Fodor, ironically. So Roman convinced me of this. Roman Feynman had a really good argument. I was like, no, that's 100% right. It's like Jerry Fodor's like the extreme anti-neural net person. And his argument for where concepts come from is they're all innate. Every single word is innate. And all the concept is an index into a thing that says I have a concept for that. And then your job as the learner is to associate it, like to populate it. And we were like, damn, that's an embedding matrix. That's literally exactly what, like LLMs, like, good job, Fodor. Like this is all you ever wanted. Like they did it. But like the reason we hate that was like, no, that's ridiculous. Like this is like Fodor's argument was meant to be kind of extreme, and people put like what the consequence that he's just like, sure, I'm going to commit to the bit is like, yes, every baby is born with the concept of carburetor, and they're just trying to figure out what word to map it to. Right. Right. So that is literally what an LLM has, right? It knows there's a thing called, I mean, it's word pieces, it's carb or right or whatever, but like it knows that these are the things. So like you've eliminated the most interesting part of the language concept learning problem, I think. So LLMs can't do that. But then this is where I think there's this proof of concept that neural networks can learn these kinds of structured representations in particular ways. And so maybe we can borrow something from that and then go back and refine. But this is where, again, I think the LLMs can be a source of hypotheses and theories and ideas, but they're not the be all end all. It's not like that all we do now is say the LLM, that's your theory of cognition, right? Like that's, yeah.
This might be an overly dumb question, but do you think this like neural network symbolic dichotomy makes sense? Because like it seems to me that a neural network is like a kind of thing, and a symbolic thing is like a way of talking about a thing. Neural network could do a symbolic thing, even if it's like literally nodes and images, whatever.
Totally.
So does this like make sense to you, this dichotomy?
Yeah. No, I think you're spot on. Like there's like the kind of debate that this falls into the levels of analysis arguments, right? So I did have a credit, like Tom Griffiths has had some really good thoughts on this, and we've been trying to work on, we haven't made it farther than saying we're going to write a opinion piece about this, so forthcoming. But I think there's in this history of this debate, there's been pretty slipperiness about this. So I think something that has been uncontroversial, and even I bring up Fodor a lot because he kind of epitomizes this, right? But like even really extreme people who say that humans are symbolic systems have said neural nets can implement a symbolic system. That's not up for debate. So there's an implementation level and then what we would call the cognitive or the computational level. And the debate in this classic debate has been a debate about the cognitive level. So is the better description of the things that humans are doing symbols or neural networks? Even though both, like you can implement a neural network on a digital computer, you can implement a digital computer in a neural network kind of a thing. And so it's supposed to be a debate about like, what's the right level of description? Some of the stuff I'm talking about are indeed slippery in this respect of like, we're kind of talking about a neural implementation of what might just be a symbolic system. But what I think is very interesting is I'm pretty sure it's not what would we call a mere implementation. It's different in important ways that will have predictive power, right? So I think this is kind of why I like calling out that's like different rules in that first section. Like it's kind of weak evidence of this, but like I don't think that at the end of the day, we'll be like, oh, this is exactly the Bayesian language of thought just implemented in a neural network. It's actually going to be, there's going to be important pieces of data that are differences in predictions that the explicit symbolic system and the neural implementation will make. And that'll tease them apart in terms of which one's a better model of cognition. So I think it could merely implement, it probably doesn't, but we technically don't know, right? If that helps, yeah.
So partially related to that question, how much does the existence of a symbolic component in the model tell you something about its outcome?
Yeah.
So what I'm saying, like the fact that you can, with a 7 billion parameter, there's lots of circuits that you can find. And does the existence of those circuits tell us something about its possible use in learning?
Yeah.
Because you know the duplicity of circuits and the fact that you can
Mhm.
find circuits that seem not to be used for any circuit.
Yeah.
I feel it seems to
Totally. I think, yeah, so there's like, it kind of depends on what you mean by causal, right? So there's like, you can run, you know, what people do right now is you run these little ablations and you show an effect in the right direction on behavior. And it's rarely like a whole effect, right? It's like this, when I ablate this circuit, it decreased the probability of getting it right. Doesn't mean it never gets it right or something. And there's all other kinds of things that people call like repair mechanisms. Like if I delete the circuit, something else takes over and so. And this is, again, I think like this is why I say like, oh, maybe we'll have an answer in like, you know, 1, 5, 10 years, everyone working together, but God, it could take like another century because this is kind of, in my mind, this level of analysis question is like, there's this kind of neural implementation, there's this cognitive level, and we're looking for something that's like the right description of all of the behavior, and it needs to kind of work out those levels. So when we talk about causality, like one thing that people really like about symbolic systems is it seems to apply causal force to these abstract things that seem really kind of, you know, like they're these abstract causal models and they're kind of like complete. Whereas when you talk to neuroscience, it's like circuits in the brain don't have this kind of causal thing. They're more like what we see in the LLM, which is like you ablate, I mean, to the extent that you stimulate something and you see some effect, but it's intertwined and it's polysemantic and it's on whatever weird things. And so like what gets assigned causality, I think is hard to say, but I think what we want is a high causality to be assigned to some high level thing. And then at the lower level, like the circuit level, we should see effects in the right direction, but it's not going to be like completely this neuron is related, right? So I think like stitching those together is definitely quite complicated. I'm not sure we entirely know what we want with a causal effect, but yeah, I don't have a better.
I guess another way of thinking about it is, would it be useful to think about like fuzzy model?
Yeah.
Thinking sort of going back to your pushback against like how.
Yeah.
It's like many of these things, they don't have some of the components that we associate with typical weakness or efficiency. Maybe you think about them in classical.
Yeah.
They're like arches of maybe sometimes you reconcile.
Yeah. I agree. I think that's what it is likely to do, right? So I think I like exactly how this looks is open, but so there's like, sometimes I've avoided word like fuzzy logic because there's a version of like fuzzy that gets assigned to like explicit symbols that have probabilities associated with them, but those still inherit the problems of symbols. What I sometimes use like pseudo symbol because it's like sometimes it behaves like a symbol, as in like maybe it composes semi-productively and maybe it allows compositional generalization and but then it's like a little bit content independent, right? Like maybe I have this duplicate token head that can detect duplicates, but it can't detect any duplicate everywhere, right? Like it'll only detect duplicates within this kind of neighborhood. And I've been interested in like logic as a really good example where people say like how domain general is like negation. Like this is Roman works on and talk about a lot. It's like, you know, you have this in a logical system, there's like one not operator that can take anything as input. It's not clear whether kids develop that or whether humans actually have such a single not operator that can apply to content of any form, right? And so those are the kinds of things that I can imagine being like pseudo symbolic. It's like it has some amount of content independence and it has some kind of weird idiomatic nature and things like that, but it also behaves compositionally in certain contexts. And I could imagine LLMs being like a really nice source of like taking this kind of hand wavy, like maybe it's somewhere in between and proposing a precise way that is.
I think we're at time, so we can.
Thank you so much.